So, good morning, am I audible?
Yes, you are. Yes, you are.
So, today, given that we have very little time, I will not delve into too much of science, but instead, I will go in and show you what I have spent all my life in developing science. Okay, just a touch of our university. I'm from KTH, which was founded in 1827. Sweden is a very, very small country with around 10 million in population, but we have a large stretch of land, as you can see there. So that's what is my university, and we are typically just like the IITs are. We are only engineering stream. Okay? Good. I will introduce you first a water cleaning device that I've been working for the past 30 years. This is what we call capacity deionization. The idea behind is very simple. Any capacitor you could use to pick out dissolved ions from a solution, can be salty water or industrial water whatsoever. And then once it is done, you can just simply discharge it. So it basically works like a capacitor. You charge and then discharge. So first thing first, one needs very high surface area electrodes, and that's where my competence comes in terms of nanomaterials and functionalization. So right at the onset, I tried to look at how people were working. They were actually putting the water on the surface of these electrodes, and I decided to put it through the electrodes. And we saw that you have additional advantages over that, and these are things that we have been able to scale it, which I'm going to discuss now. Instead of going in for very complex models in order to understand what was happening, we developed a very simple model from language absorption that could be actually used for scaled up systems. And then we furthered it to automate it in order to tune it and predict what we can do with a certain surface area of the electrodes that we have. Following this, we try to focus on if we have a mix of ions, what can we do? And today I can say that we have a fair idea with our models to understand what any given device under the current configuration would work. But this whole journey started in 2006, and only in 2018 we were able to spin off the company. In 2019, sorry, and this is a model that we came up with, which was the first commercial model in 2022. So it takes decades of effort in order to translate science into a technology. So what is it all about? Basically, this is a technology that essentially manages to replace multiple technologies with one. It can do deionization, precipitation, so avoid chemicals, and it can also remove germs in a sense, because as the electrodes are made of carbon, bacteria and fungus, they do attach very nicely, and also one can do removal of color. So this is a technology that will be developed that uses minimum chemicals. It's just for regeneration of the electron, time and off, we use that. It has no membrane. It has very little operational complexity, and that translates to lower cost. But as a scientist, we are never happy. Once we are happy as a scientist, I think our career is done. So I am currently looking at can I translate the same technology into sustainable treatments? Like we have one experiment going on at quasi prototype level where we are trying to convert nitrates that we get from fish pond into ammonia. Okay. I will just touch base on the new exciting thing that is going on in the lab now. This is a new kind of electrolyzers. So this work we started during COVID. Actually, it was designed in the hospital when I was quite badly hurt. And then we started to look at it from there with the basic thing that 90% of hydrogen used today comes from fossil fuels. And in order to reduce the CO2, one has to come up with new scalable green hydrogen technology. So if you look at the IIT's research, they have come up with a pretty nice cycle of things that we need to do. We need to reduce the critical material use, standardize materials and system design, improve the electrolyzer efficiency, which is plagued with the fundamental issue of thermodynamics. We have to look for electrolyzer with material durability and compatibility. Electrolyzer safety is often overlooked, but it's very, very important. And to simplify the design so that manufacturing and system costs can come down, and it's ready for mass production. So, I'm sorry about the spelling mistake, but it's ready for mass production. So essentially, we have this whole cycle of things as researchers we can contribute to. So what I was thinking is that when we split water, as we learn in school, that if you just have two electrodes, I remember having done this experiment at home with salt water and graphite leads from pencil, then you can get bubbles on both sides. Where the cathode, you will get the hydrogen, and the anode, you get the oxygen. So if you look more carefully into the current voltage characteristics, the HER, it happens in the negative regime, OER in the positive regime. So if I have a single electrode or a bifunctional electrode that does both the HER as well as OER, then I do have a possibility to play with this voltage range in order to decouple the production of hydrogen and oxygen. It was easier said than done, so we kept struggling with it for the next 2 years, but ultimately in 2023, we did manage to make what we call the first supercapacitive electrolyzer in the world, in which when out here essentially we have an energy storage electrode and a bifunctional electrode. So when we produce hydrogen, we store the energy or the oxygen in the electrode and then we reverse it back. So what has happened with this? We got rid of the membrane. So immediately you get 30% of the cost. It's easier to talk about for a small 10, 20 milliliter hydrogen production. But
2 minutes.
I'm happy to inform you that we have been looking at the long-term sustainability and of the electrodes. And if you look at it, the electrodegradation is minimal, which is very surprising. We still don't understand the science, but we have made a 1 kilowatt unit now, and we are moving into a 5 kilowatt unit at this moment that I talk through my startup in order to make this 2 kilogram of hydrogen, $2 per kilogram of hydrogen a reality. So with this, I think I will have to thank my students and thank you very much for your patience and listening.